And just, I can't see anybody anymore because of my monitor setup. So just let me know when to start.
Okay, will do. All right, so I think we're going to get going. So I'll start. So we're really, thank you everybody for coming to the PRAIRIE Colloquium today. We're really happy and lucky to have Matt Post presenting to us today. Matt has been a research scientist in the Microsoft Translator Group since 2021, having previously worked at the Johns Hopkins University. He's been involved in a number of quite influential machine translation and generally natural language processing projects, and also as the director of the ACL Anthology, which is the main hosting website for papers in NLP, for those who aren't familiar with it. It's thanks to him that our access to papers and BibTeX entries is so easy. So today he'll be talking to us about contextual translation. So Matt, yeah, the virtual floor is now yours.
Okay, thanks, Rachel, and thanks for the invitation. Hi, everybody. Thanks for coming to the talk. I guess I had my notes up, so I thought I would start out today by addressing the elephant in the room, what happened to my face. I had a little bike accident, going too fast, turning too sharply on the streets of Baltimore. Asphalt is very unforgiving, but I'm fine. So no need to worry about me. If you are worried about me, you can take it easy on me in the question and answer period. But please feel free to interrupt with questions anytime. Remember, I can't see you, so I don't know. I think Rachel's going to raise questions that come on in the chat, or just interrupt me until I stop talking. So today I'm going to talk about work that I've been doing with my colleague Marcin Junches-Dubman at Microsoft. And the question is, why are we still translating sentences? And I hope I can make the case and maybe convince people that we can maybe actually start moving to doing a full contextual translation. So, there's a number of different use cases for machine translation. I think the dominant one is probably actually translating documents, right? When people might use it for translating sentences here or there, or actually, if you look at the Google Translate console, people use it for translating words, maybe in language learning or so on. But at least one big use case is, say, translating web pages, and so that you can read them in your native language. And as everybody here probably knows, what actually happens under the hood is the sentences in a document get split up, or the document gets split up into these sentences, and they're all translated independently, which is indicated here by color coding. So in research settings, this is done for us, so we actually don't even deal really with the sentence splitting part. So we don't even really, we're, I guess, another step removed from that. But in production settings, of course, this is what's going on. So I don't think I need to make the case too strongly that this is a problem. So I have a couple of different examples here. Probably the most studied one is dealing with anaphora. So on this bottom example, we have a German masculine noun, but then the wrong pronoun gets chosen in the second sentence because it just doesn't have the context to translate it correctly. And there's lots of different other examples. So we could look at disambiguation. This is an example where the system translates bat incorrectly into French because it doesn't have the context that this is happening on a baseball field. And then there's also sort of lesser known, or maybe studied, partially just because it's really difficult to study, but there's issues of consistency, right? So you could translate a document. This is simulated. I couldn't actually get an example to mistranslate this. I think the context cues a formal register too strongly. But this does happen, right? So you get one sentence in a formal register, another sentence in an informal one, and it's jarring to read and just incorrect. So basically, the paradigm we're working under fundamentally limits our ability to produce good translations, and it raises the question of why are we doing it this way? So there's lots of different reasons. I'm going to talk about three main ones that we've been working on addressing all at once. So I think the first one of these is just, there's a big question about architectures, right? So what is the right architecture? What should we be using to translate documents? Second question is, this is maybe the biggest practical one, is there's just not a lot of parallel training data with document annotations, which is what we need for training document systems. So we have all this parallel data, but not the document ID, and it actually goes even quite a bit deeper than that. But the fundamental problem here is data. Okay, so why don't we have document IDs? Well, it's sort of, I think, just sort of baked into, we're sort of really deep into this sentence-based paradigm, and because we're in it, we kind of make further and further engineering assumptions that get us better translations under this paradigm. So, in standard crawls, they're not really retained. In PRAIRIE, I mean, you do have the raw document dumps at some point, which have document information, but it's everything is sort of geared toward producing a TMX or a by text file without the document piece, including steps like deduplication, which are inherently sentence-based. And there's also, because of the fact we're just going after sentences, it allows approaches that make use of comparable corpora, right, which you couldn't use in a document setting because they're not actually translations of each other. And then we also have, some modern approaches, really going all in on the sentence-based paradigm, and just throwing out document IDs really early in the process and doing a full comparison at the sentence level to try to sort of extract every last drop of sentence parallel data. So that's the second reason is data, and a third piece is evaluation. So we have sentence level evaluation down pretty well. So it's been continually improving over the years and changing, getting better. But it works really well at a coarse granularity. We know how to do it. So I think Blue carried us really well through rule-based and statistical areas of MT, other surface metrics like character F as well. Nowadays, we're moving to more model-based metrics that are better at discriminating really fluent neural systems. But we know how to do this sort of evaluation at the sentence level. They're pretty decent at doing this kind of coarse level discrimination between systems and telling us, should I deploy this new system or not, which is kind of the basic question of evaluation. So I think the reason we're still translating sentences is we're kind of in this rut, right? So in order to start translating documents and actually do this, you sort of have to change all these things at once, right? So we need to figure out what the right architecture is, but if you come up with an right architecture, you can't really train it because you only have a small subset of your data which actually has the annotations. And then even if you can train it, it's hard to evaluate it. So you really kind of have to change all three of these at the same time to get large scale data, to figure out what the right architecture is and to know if you actually have a good system. And doing that all the time, is pretty hard to do. Or sorry, doing that all at the same time is pretty hard to do. So other reasons that I'm not really going to talk about today. So there are other reasons not to do document MT. So it's slower. Translation speed, latency tends to be, roughly linear in the sentence length at the lengths we work with. You could argue that there's diminishing returns. Maybe the phenomena that are addressed by document level MT just aren't frequent enough for us to merit all the additional complexity that get introduced in building such systems. And then you could also argue, maybe it's just not worth it. I guess this is related to diminishing returns. But maybe you just don't need it for the standard use case. So, people translating web pages, you can get a pretty fluent web page, and if it gets the formality incorrect here and there, it doesn't really affect your interpretation. So, it might be that document MT is largely, it's a fluency issue, and fluency tends to be less important. All things considered. Okay, but I'm not going to address those things. I'm just going to assume we want to build the best systems possible. What is it going to take to get us there? So the findings today are three parts. So it's going to address these 3 points I raised. So the first one is just an argument for the basic transformer architecture with enough capacity, and to say that this architecture is sufficient. There's no need for fancy architectures. Let's just use the basic transformer, which has had so much success in other places. The second piece is to solve this the lack of document level annotations just by punting. So let's not use document level annotations from parallel data. Let's just use it on the back translated data. So we can more easily identify monolingual data with document annotations, back translate that, and then that's our pool of data to source documents from. And then the larger part is I'm going to make an argument that we should be doing generative evaluation instead of contrastive evaluation. So this is actually the hardest part of the talk, and the part where I think we've made the least progress. It's really hard to evaluate document level MT. It takes a lot of effort to put together the data sets and the evaluation settings. So we could make a step forward, I think, by trying to do some evaluation on the actual outputs of MT rather than its ability to discriminate. Okay, so I'll elaborate on all three of those. So basically summarize, we're looking for architectures, data, and evaluation. Okay, so here's just a picture of contrastive evaluation. This is from a paper from Rico Senrich's group. So this is the Contra Pro data set. So basically what you have is a naturally found sentence pair from open subtitles. So you have this English source and then a reference that's been translated, and it's focused on pronouns. So what you do is you take the correct pronoun, which is Z, and you put in both er and s, and now you have these two pairs, the correct one with each of the incorrect ones. And you can feed these into your machine translation system as pairs in scoring mode. And you look at the model score that's assigned to the correct pair and each of the incorrect pairs. And if you get a higher or better model score on the correct pair, then you get a point. And if you rate them incorrectly, you get another point. So this is actually really a nice way to sort of conceptualize performance and to apply it at scale. So when you see, you get a bunch of sort of metadata here. It's labeled here with the word in English, so we know what the word is. You know what the translation was in German, and then you know how far back the antecedent was. So this is a big data set with about 36,000 pairs in total. So I'm going to look at a bunch of different metrics. So the first one across a couple different language pairs. So the first one here is this Contra WSD data set. So this one is actually, it's not really designed for document level evaluation. It's just designed to test a system's ability to solve the word sense disambiguation task. But you can try to see if document level context, it's built on open subtitles data, so you can see if context would help you, increase how well you can resolve these disambiguation problems, because the data was annotated really nicely. The next one is the Contra Pro one I just mentioned. So it's actually 12,000 instances, but then you compare it with each of the incorrect pronouns to make 36,000 total. So that's for English German. So for English French, there's a couple that we looked at. So one is, this first one is Disc Eval MT. So this one is a hand-built corpus. And I'll have a bunch of examples, and it's a bit smaller, but it's basically designed to test a model's ability to solve lexical choice and anaphora problems. And then there's a bigger one that was put together later. Rachel was involved in this as well, for English French, and this one is basically Contra Pro for French. So it's open subtitles data again, lots of different instances where you're trying to predict or score the correct pronoun higher than the incorrect one. And then for English Russian, there's a data set with lots of different instances covering lots of different complex phenomena in English to Russian translation. So here's some examples. So Contra WSD, we have, these are produced by taking the correct word and then inserting, if you look at the upper left for Contra WSD, so you take the correct translation of the word absatz and you put in incorrect word senses. And then you want to see if your system can assign a higher score to the sentence with the correct one versus the incorrect one. So the Contra Pro, you've seen that one in the lower left. Here we have, the correct pairing of a pronoun with the incorrect versions. This is, again, is all found data. So the Disc Eval MT, so this one is mostly, it's inspired by data, I think, if I understood the data notes correctly. But then it's sort of contrived examples where you have like the setting right here, so you can see the source sentences. So you see how bad the implications are. Yes, they're quite devastating. And then you have two different French translations of the word implication, which have different gender markings. So then you force decode basically well, so sorry, you score the version, you can kind of take the whole cross product of this, and the versions that are consistent, if you score those higher than the versions that aren't, then you get points for that. And then for the good translation wrong in context, this is English Russian. And here, this is an example where I think this is formality. But did you conjugate, formal or informal you correctly? Okay, so that's basically, we needed to start with how to do this evaluation, because it's going to come into the talk when I talk about how we first started out approaching this problem. So I guess I'm going to do a little bit of a chronological walkthrough at how we sort of went about this project, which I think is a little bit instructive instead of just kind of presenting it as if we found the results out of nowhere, and kind of shows charts how we kind of broke some of this knot and came to some of the findings we have. So I think that this argument for doing the first piece is the architecture piece, right? So we don't have strong arguments for, well, I guess actually I think we do have strong arguments for just going with the base transformer architecture. But I don't have, what I mean is I don't have empirical findings. So we didn't actually implement or experiment with lots of other different architectures. We basically just had it as a premise that we should be able to do really good machine translation at the document level with the standard transformer architecture. And I think that finding is, so part of it goes back to other work that was done, work that Marchand did in 2019 as well. And there's also just the evidence, I think, from large language models, right? So we've seen all of these large language models are just built on basically the standard transformer architecture and are doing, extremely document. I mean, it's at root, it's document-based modeling. So there's no reason to think that we shouldn't be able to do this for machine translation as well. So that was kind of that we started out, and we've only worked with these architectures. And then the question is getting them enough data and making sure there's enough capacity. So for starting out in this project, we just in general, we have a 12-layer encoder, 6-layer transformer. Model size is 1,000 roughly, and then we have a 16,000 size feed-forward network. So we use virtual epochs. This is using the Marian toolkit. So we train it for 40 epochs, where each epoch is defined as seeing a billion target tokens, using a batch size of about 500K, and then a bunch of other parameters which are more or less standard. So the thing today that might be a little bit unsatisfying is I'm going to talk mostly about a private data collection that I can't talk too much about, but which you can probably guess the nature of. I will say a little bit more about size and so on in coming slides. But so this is basically the pictures. We have, as you can imagine, a large pool of parallel data and a large pool of back translated data. These icons made a lot more sense to me when I first chose them. I don't know what they are. Oh, I know. It's a natural, parallel data is natural, right? Yeah, this doesn't work at all. Anyway, the ocean is the parallel data, you find it. The unnatural data is the back translated data, which comes from a fire hydrant. Anyway, the model is we have these two pools of data, and we have a tool that basically just loops infinitely over these pools and randomly at every instance chooses a pool, chooses a target length, and then we have document identity. This private data collection has document IDs on both sides, and we just choose a length, and then you fill up to that length. You just join sentences until you reach the length, and then those get fed into the trainer, and then the trainer loads up a big, this is Marian, it loads up a big batch, and then it does sorting within that and builds the batches for training. But it's all done online and dynamic, so it avoids having to load all of the data into memory at once. So here's what it looks like. We have, I guess this is the only document annotation we use. So we have a 32,000 size 32,000 joint vocabulary, and so we just join with this EOS token. So this is another sort of architectural design that people experiment with. You can do a lot more fine-grained tagging. It might be something worth doing, but we started out and have just been using this simple tag. So when you join sentences, you put this EOS token in, and it's inserted here so as not to create extra tokens. So you see when it gets split off, it doesn't create if you actually add a space around it, you'll get extra tokens depending on what your sentence piece settings are. Okay, so then what we did was we started out doing evaluation. So we have sort of our publicly available system. So this is just, I didn't write this. This is WMT 21, which has some document level annotations. So we look at the blue score we get. We look at the blue score sentence level system gets, and then what the document level system gets. We do the same with comment, which we trust quite a bit more. So this works, right? So this document system is doing, it's doing at par. It seems like it's better trained than the sentence level system. And it also seems like it's doing really well in Contra Pro, right? So these are pretty good Contra Pro scores. It's much better than the sentence level system. So we passed these 2 checks. But then what we would do is we'd feed in sentences. Like here's this on the left. So where's my hat? There it is. And then we translate it and we would get S. And this should be air because hat is masculine. And we did tons of things like this. So what we would see, for example, is like if we put a semicolon or we took out the EOS token, it would work. But if we put a semicolon in, it would work. And partially, it's because these would be sentence internal, like it would have seen instances of these, just sentences that didn't get split in the training data and so on. But partially, it seemed like what was happening was it was learning that this EOS tag was not reliable for figuring out what the pronoun was. It wasn't looking past it. And here's the that should be green there. Yeah. So in this setting, it would get air. That should be green. And so this was strange, right? We did really well in Contra Pro, but now when we're trying to actually get translations out of this, it doesn't seem to be working correctly. And hunting down and looking at this, it seemed like what we found is that our crawled parallel data clearly contained a lot of MT output. You could see this with word sense disambiguation, where we get the wrong word sense. You could see it where where it get the wrong pronouns, and it wasn't all the data, but it was enough of it that the system was either learning bad patterns or learning not to trust the good patterns it saw. It was a source of confusion for the system, and so that led us to think that the obvious conclusion is we need to do a better job of selecting the parallel data. So it led to some follow-up experiments. So here's a picture of our data. So this is a subset just of an internal research purpose data. The mono data, I mean, it's mostly crawled data from sources you might expect. These are all data sizes in the millions. So we have large pools of crawled data for different language pairs. And then we have, for mono data. And then we have the parallel crawled data, and then we have CC matrix. So CC matrix doesn't have any document annotations. The crawled data does. And then this yellow bar, like the heart of the crawled piece, that just tells you what percentage of the data is actually has document annotations. So you can see it's really most of it. Most of the instances are part of a document. And then over there on the right, you can see the mean document lengths. So in general, the parallel documents that we get the document annotations we get from crawled data are much shorter on average than you get from the mono data. So this is a picture of the data that we're using for our experiments. So part of the reason we have to do this on internal data is because it lets us do this full set of experiments that we can't do on the outside. So I will have an experiment from WMT later, but I can't do all of these systems. So I can't do anything with documents sourced from parallel, at least not at scale. So I'm going to have a number of different models that we're looking at. So we have this baseline sentence model. So these are all trained. You picture that the picture I gave where we're mixing data. So it's all the same data. There's just a flag of whether we are going to allow documents to be sourced from it. So the sentence, everything is just sentences. We never join models, or we never join documents. The sentence star one it's the same model, but indicated here to show that we're using it to translate documents. So sometimes the test data will be document level. And then we have basically 3 different document systems. So one takes documents from both pools, and then the other 2 take document just from the parallel data or just from the back translated data. And the system we're training is basically trained up to 250 tokens per sample, batches up to 500K. And so here's the sort of slightly modified picture. So we do choose a pool, choose a length. If documents are enabled on that pool, then we join sentences. Otherwise, you just take the sentence that you get. Okay, hopefully that's all clear. I can't see anybody, so just a reminder to jump in if you have questions. And this is basically just a sanity check. So we have our baseline system again, and then in all these internal systems, just translating at the sentence level. So that they're all pretty equivalent. Although we're seeing some small improvements in the document system. This is on WMT 21 data sets, except for English French, which is WMT 15. Okay, but now we have a new problem. We have the MT output is gone from the training data because, at least in this doc back translated system, it passes the sanity check. So, but they're all equivalent. So, so by the sanity check, I mean this custom thing where we were just giving it handcrafted sentences and seeing if it would get the pronoun correct, for example. So in our updated thing, only this document. Actually, can you guys see my mouse or no?
I'm not sure I can see it. Can you wave it around? Yeah, I can see it. Yes, yeah.
Okay. So this document level system here, where it trained just on the back translated data, is passing the sanity check. These two are not, but the ContraPro scores were all the same. So we do have sort of an internal. This makes sense. They're all doing better than the sentence level system. Even the sentence system employed, to do scoring, even though I never saw training data. That's the CentStar one. And then, but all these systems are, I don't know, there's gaps, but it felt like these were all doing, this gap didn't seem that meaningful. So this led us to think that maybe doing this contrastive evaluation wasn't the right approach for it. So, and here's my analogy. So looking at this picture, who do you think has the easier task? Is it these guys on the bottom or the guy on top? Which we could talk about as the guys on the bottom doing evaluation, evaluating the guy doing the work, or the guy on the top who's doing something pretty difficult to do, pretty fantastic. So nobody has to answer out loud. I'm not saying evaluation is not hard. Evaluation is very hard. I couldn't rate these guys. I watch gymnastics when the Olympics come on, and they all look really good to me. Evaluation is a hard task. But I think if you had to say which of these is harder, we'd probably have consensus that flipping through the air like this and landing without breaking your neck is significantly more difficult than doing evaluation. And I think you could apply the same idea to machine translation as well. So the question isn't can the model discriminate good outputs from bad? That is an important question. You should be able to do that, but really the question we care about is whether the model can generate good outputs. And so what we did is we basically transformed all of these metrics into generative variance. So where we compute accuracy. So I have to say this was much easier than it could have been. It was basically possible because all this data was annotated so well. It's a really nicely formatted JSON data structures where all the words have been identified. It was really nice to go through these data sets and basically produce generative variance. So I'm being a little bit vague here about how to compute accuracy. So basically, let's take ContraPro, for example. We tokenize, we generate the output and then we tokenize it all. We have that EOS token, so we can grab the last sentence and we just look to make sure, we check if A is in it and also make sure that S and Z are not in it. So we know the correct answer, we know the incorrect answers, and we just have this kind of strict check where we check that the word we want is in there and none of the words we don't want are in there. And if you get that right, then you get a point. So, is this a perfect metric? No, because for example, there might be multiple pronouns, right? Maybe you get credit for something that was actually referring to another pronoun. There's also examples where a system can, especially with S, you can reword a sentence and produce a correct translation, but without using the pronoun that you're supposed to use. So you'll get dinged for that under this metric, but it actually works, I think, pretty well, which we verified in a kind of spot checked way. So in the end, we get basically generative variance of all these models. So here, basically what we do is we take the same system before. What's this? Okay, so what I'm doing here is reporting, these annotations also included the distance the antecedent was, so we can discriminate between intrasentential, which aren't that interesting because the sentence systems do really well in them, and extrasentential. And I'm reporting, anything that was beyond, what required some context. It wasn't answerable within the current system. Okay, having said all that, the German-English system is an exception because, as I said, this is the contra WSD. It's a word sense disambiguation task. It wasn't actually designed to use context, but we can use it. I think the notable thing here is that the contrastive systems, basically everything does really well. If you build a big enough model on enough data, you can really nail this contrastive task. But we do see with this, I guess we're seeing the same thing basically in the generative setting. So this is also a little bit of a stretch with WSD because you're looking for the right word in the output. But again, with word sense disambiguation, it's even this problem of translating something correctly without using the word you wanted it to use is even bigger than with pronouns. But you do see this. So basically, the sentence level ones and the document ones are all doing the same. So I do it here. We have a German-English system because I wanted a language that I could read natively and make judgments on, and I'm presenting it here because this has bearing on some of the more morphologically rich questions later. So if we look at English-German, so this was the motivating problem. Here we had contra-pro, the contrastive test set. The models were indistinguishable, and now we get a pretty clear gap with this system that again passes our sanity check, but failed. We're getting a much nicer gap between the system, which we are pretty confident is good, in these ones, which we think are not good. And that's carried over to English-French. A little less so, right? These baseline models seem to be doing better. I'll have more to say on that in a little bit. But we do get this bump from training on back translated data only. And then, so for the English-Russian one here, there's a couple differences with this data set, but the results here are not nearly as good as they are for contra-pro, for example. Russian is the language I have the least to say about today, just because it's very hard to do the analysis, especially for me. But I think part of the problem here is that you have what you're looking for in this accuracy metric is a very particular form of a word, and there's lots of morphological complexity that determine what the correct form is. We're looking for an exact match. We're not doing any kind of morphological analysis or anything. Okay, so for English, French, and German, here's a breakdown by pronoun and distance. So I think an interesting piece here, so let's just look at all pronouns, is that this is the system, right, trained on parallel documents from parallel and back translated data. And this is the one on just back translated, and they're basically even. You can see this basically in all categories, maybe not L, but for il, and so on. They're pretty equivalent. In Germany, see the same thing, right? They're pretty equivalent on their ability to resolve questions when the disambiguating context, the anaphora, is in the current sentence. That's what you expect. But when you go to distance greater than 0, that's where this distance starts to come. So the only difference is, this, well, I'll call it the quote unquote bad system, the parallel and back translated one, seems to do better on, like for German on S. So this is basically the predominant case. But overall, it's doing a lot better on the generative metric, and especially with the minority grammatical pronouns, it's a significant boost. And I don't know if it's fair to say that il, the masculine plural, is sort of a predominant case in French, but if you buy that, then we have a similar pattern here, right? So we're doing better on il, much better on L, which is probably the minority, and much better on the plural version as well. So I'll show you a bunch of examples now. So this is exactly what you might expect. So here's an example. I believe this is from Contra Pro. So here's a big sentence, right, where it's the baseline system is just getting all of these wrong. S, they're all wrong. Except for this one. This one is not related to the anaphora. But the back translated system gets this correct. It has Z instead of S. Another example for, let's see, this is, yeah, English, German again. I guess I didn't color these, but once again, this is, I don't even know what this word, a molecular nanoscalar, I can guess, but you see here we're getting, baseline system guesses S, but it's actually air. A few examples in French. This is distance, I guess the anaphora is 2 sentences before. So it's getting, baseline system gets il instead of elle. And then we have more examples, right? So I see the light. I think I have these systems reversed. Yeah, I must have these reversed. So the parallel and back translated system gets the case or the gender wrong, and also the corresponding adjective. The back translated system only gets them both correct. So, okay, so those were source side document metrics, where the question of disambiguation is entirely one of the source side, right? So it's just standard translation. You give it the source side document that's all been merged. You translate into the target, and then you have the whole target. But there's a couple other types where what you have to do, or basically the disambiguation is a function of words you've already translated. So that's a different setting for this generative evaluation. So we have this target site context, which is consumed. Here we consume it as a translation prefix. So basically we force decode to it. I guess I don't have an example here, but you can imagine if you have the example I gave earlier where you have an ambiguity in how you translate a word, and maybe you're going to translate it masculine, maybe you're going to translate it feminine. And depending on what you pick, the second sentence in the target has has to be consistent with that first choice. So we hard code, we basically force decode to the one of the choices, and then check whether the target site gets the same thing. So here's the contrastive evaluation. All these document systems are doing pretty equivalent. And here we're seeing something much different. So the generative variants are basically not distinguishing themselves very much. This is true for English, French, and English, Russian again. I'll put all these up. So it's hard to say exactly what's going on, but I can present a couple guesses about this. Let me show you with some examples. So, but basically, the takeaway to keep in mind when I go through the examples is, the contrastive systems are all doing pretty equivalently, but then when we test them on their generative ability, they're also doing pretty similarly. So one explanation, I think, might have to do with the fact that, well, let me look at examples while we talk about this. So here's an example. We have the people who did this are really despicable. I know, how could they leave the room in this state? And then the system has provided context that it has to force decode to, right? So here, if we choose individu in French, that's masculine. So you want the second translation to correspond to it in terms of gender. Whereas if we chose les personnes, then it should be feminine, but it's not. This is the translation we get out. But if you do, if you sort of stretch the translation of people and give we get il correct, and the system does get l correct when you do femme. So the absolute numbers are low, but it's not entirely ignoring this context here. So it's hard to say exactly what's going on. I mean, here's another example where this is another alignment issue where you give it the context. It has to translate lemonade twice. You want it to use in this setting, you want it to use citron pressé. Here it chooses limonada instead, and then here you want it to use this. You sort of have this baseline case that it sort of defaults to. So we don't have a lot of deep analysis of this at this point. It might be that the priors are too strong. It might have to do with the fact that this is sort of unnatural data, since these examples were sort of all made up. Maybe there's just not that many instances of this kind of cohesion in the training data. So I think part of the motivation for this sort of lexical cohesion task is that if you have a word, you want to translate it the same. I think that's generally true, but there's also situations where, for purposes of good writing, you want to not use the same word every time, right? you might want to use introduce some kind of variety and so on in the translations. So maybe, the phenomena, it's split enough between those two that there's not a pattern that the decoder can pick up. Maybe we didn't need a different architecture, I don't know. But these situations we're not doing as well on. And here's kind of an example where I think maybe, I don't know the subtle senses of these French translations well enough, but maybe this would read better if you had different, you want to emphasize how angry she is, so use a different word. I don't know if that works in this example or not, but maybe the point can stand as well as that maybe you don't actually want cohesion in a setting like this. And here's another example. So there are settings where you can make these work. So this, if you give it the right context. So this is another example from the DISC-eval MT dataset. So the second example right here is the one that it fails on. So you say, could it be anything serious, doctor? We'll have to get rid of that mole. So I think to a human, this clearly triggers the skin sense of mole, but the system gets it wrong. It chooses taupe. But if I change the wording, if I put face in there at all, or if I change the context even, the doctor closely examined my skin, we'll have to get rid of that mole. Here it gets the sense right. So it might just be that this is, I don't know, too much of a stretch for the system, or this might have to do with the nature of the data, I think, being manufactured instead of found. You need a lot more investigation to see what this matters. But we sort of have this base prior. I mean, another thing we could do that we haven't done is look at the scores here. How strongly does it favor taupe over the alternate translations? So, but it's not just that it can't translate this; it can with the right context. And here's another example. So, the base translation here for record is dossier. It gets it right if you give it this this translation. In this setting, I think this word is maybe correct, but it's not the one the system is looking, or maybe it's arguable that it's okay, but it's not the word the system is looking for, which is dossier. So it doesn't get credit for it. So this kind of goes back to the contra WSD task where when the set of words you're trying to exact match is too big, doing generative evaluation is a bit more difficult. Okay, so I also want to look at, I'm going to look kind of piecemeal at a couple different settings. We haven't seen a ton of improvement, at least on WMT data sets, when we do document translation. So in this setting, what we do is we have document annotations on the test data. So you give it to your system, and you give it the documents, and then you split them back out and do sentence level evaluation. So most reported systems will find improvement on these metrics. We haven't found a lot, at least not at these capacities and not at these test sets. Different test sets maybe that are a bit more natural, not just news data that's relatively short. We do see these kinds of improvements, but not as much on WMT 21. So this is the doc back translated system only compared to the sentence one across a number of different test sets. This is a point about model size. So capacity really turns out to be pretty important. So it's pretty common in a lot of document OT research to use standard transformer sizes. Here we've sort of looked at a lot of different models. So this is we're fixing the decoder number of layers to be 6, and we're just changing the encoder layers and the feed forward network size. And then you get a sense of how big this model is. And you see basically all these metrics improving. So blue goes way up as you'd expect, comet goes up as you'd expect, but also our generative metrics. So down at this level performance, if we'd done this work with a standard transformer model, we might have been tempted to conclude that it wasn't going to be able to solve this problem. But as soon as you go to much larger capacities, the system is doing much better. So I think it's a critical piece of this, which you might expect. I mean, if we're arguing from the large language model perspective, those models are huge. They're much bigger, and that's proved to be pretty important for handling that kind of document level phenomena. Okay, so next question is one of context, right? How much context matters? So here we're again limited to the 12 layer system with the back translated only, a kind of default document system. And this shows you the effect basically on the GenPro metric. If you, based on how much, basically what your entire sentence budget is, so how many sentences are you going to include, including this quote unquote payload. So basically you say your sentence budget is 1, that means you can only include the sentence under consideration, and you have no context and you're going to do very poorly. If your budget's 2, you can add a sentence of context right here. And or you can just do 0 sentences of left context. So basically what happens is you get a sentence budget, you choose how much goes to the left context, any remainder goes to the right context. So basically all of these points are saying that for the generative version of the anaphora piece, right context does not matter. It doesn't help you resolve the question, which makes sense. I mean, you are getting some slow gains as we go up and add 9 sentences here of right context. But what really matters is at any point, operational point in this grid, should you go down, adding another point of left context, or should you go right, adding a sentence of right context? For this piece, at least, what you really want to do is add left context. And you can see that the numbers really start to saturate. I mean, they're continuing to go up and up, even as you add 10 sentences of context. So this is one phenomenon, one data set, and it's hard. And the data set, right, is sort of short sentences and so on. So it's hard to say. Probably right context is going to matter more for issues of style and so on. But this is looking, it's very clear that you need a lot of left context to answer these anaphora, and that adding more and more helps more. And here's another view of it. It's basically the same graph, but now, sentence budget is hard to operationalize because 10 sentences could be 1,000 tokens long. But now what we do is we fix the token budget, determine how many are going to go to the left context. So you subtract that out, and then you subtract out the payload length, and then the rest goes to the right context. And you can see it's basically the same patterns, but you can do pretty good even if you're just translating up to 150 word tokens. If you give 150 of those to left context, you've got up to 150. So you subtract out the payload's length first, and then it's up to 150 for the left. So if the current sentence was like 2 tokens, you'd have 148 here for the left context. Okay, so finally, I have a WMT experiment. So this is, I'll go over this. So it's the parallel data. This is the standard parallel data you can download. I'm doing English German here. This is just for comparison. So we have Europarl v10, Paracol data, Common Crawl, basically everything you throw in from the WMT page. And then we have mono data. So what we did here is we took the news crawl data, which is the only data with document annotations, and I just took even years from 2008 to 2020 to get about the same size of data as I had in the parallel data. The metrics are here. So we have about 14.1 million docs of about 20 in length. And then I trained these under the same settings. So it's a 12.6 model, 16K feed-forward network, I think 1,000 model size, excuse me. And we trained it for 40 virtual epochs. So we saw 40 billion target side tokens, batch size 500K. And these are the results we get. So the reason we can't do this on all data is because I don't have the parallel data, so I can't do the contrastive experiments with these other models. But you can see, so this is from a paper we're writing, but this is the sentence system. So this is the best number from our data, just for comparison. So the WMT data, we're getting lower on Blue and Comet. We're getting a little bit better in ContraPro and GenPro with the sentence system. And then here's our best English German system from that from what I presented earlier. And this model, right, it's doing a little bit better on Blue and a little bit worse on Comet. But it's getting this big bump in ContraPro, and it's getting a big bump in in GenPro. So it's following the same pattern, at least for these two systems. So I see this as a sign that we could be doing this with open data, and maybe move in a direction where we try to add this data to parallel data as well. Okay, so summary. So this is just repeating from the beginning. So we don't need fancy architectures, right? The transformer should be sufficient as long as you give it enough capacity and enough training data. That's not to say that we couldn't do a lot better with extra architectures, right? Or with sort of changes to the standard transformer architecture, but it seems to stand to reason that we can just make do with the same stuff that people are using for ChatGPT or GPT-3 and so on. We don't need document level parallel data. It seems like you can build pretty good document level systems without it, just back translating monolingual data. So there's a lot of questions open here, but I think this is at least interesting that if you do this at scale, you can get good results from that data. We do need better evaluation. So I think moving to this generative approach is pretty helpful in getting discriminating between these various document systems over the contrastive approach. But there's a lot of questions here, right? So we don't know how to make the scale. We still have these just for particular data sets. We really, this question is far from solved. There's a lot of work that needs to be done in evaluation in general. So here's a handful of just sort of future directions and so on. So a big, I think, hole in this talk is the lack of any human evaluation. So we do have human evaluations that show improvement, especially on these phenomena, but it's not as straightforward as prior work in doing human evaluation, just redoing standard metrics and seeing improvements across the board. So we see that the document systems fix a lot of things, also sometimes introduce problems like kind of summarization problems and so on. But it's also it's hard to know, because when you're evaluating these, it's actually pretty quickly clear which is the document level system based on things that you just, even if you're doing new data, you can very clearly see the things that document level system is doing, and it makes it a little bit difficult to discriminate them or evaluate them in an objective fashion. So there's lots of work here to be done on the human level evaluation piece. So another question is, ideal tag structure. There's work on this. What seems really compelling to me is you give it a raw HTML document, or maybe it's something that's simplified. But if you have, the lists, like the fact that you're translating a list should be important to the MT system. Maybe with enough capacity and training data, it can figure those out automatically. But all of this kind of metadata, it seems like, could be helpful in producing translations. The evaluation piece I talked about a little bit, and better architectures. Another piece would be nice if we could identify trustworthy parallel data, so we don't have to just throw it all out. That was kind of a first level pass, but obviously it's not all MT output. And then I guess there's sort of an operational question is, whether the gains that get produced will be enough to justify the increased latency that'll certainly result. Okay, that's all I have prepared today. So thanks for the invitation, and I'd be happy to take questions.
So thank you so much, Matt, of your talk. Any questions, you can unmute yourself. I'm not sure if there is a hand raised feature, or you can write in the chat. So Matt, I'll let you take questions if you can see. So we got Salvador, I think, first.
Hi. Hi, Matt. Thanks for the talk. So very interesting. I'm Salvador Mascarenas from École Normale Supérieure. I'm a linguist. I have really a comment, not really a question, but I think you may find it useful. So it seems to me that the significance of what you're doing is far greater than you're allowing. So it's kind of a accidental fact about our Indo-European languages that the sentence is an extremely important and exalted construction. There's a lot of languages out there in the world that have very impoverished sentential syntax, or very little sentence syntax. So for example, the languages of Greenland, in particular West Greenlandic, that the linguist Maria Bittner, Bittner, has studied. She argues that basically the sort of least common denominator, meaning-wise, in the language of the world is not at all the sentence. It's just a sort of a product of Indo-European properties, but rather the paragraph. So a concrete example, lots of languages of the world, these ones in particular, do not have the construction if-then, which English and German and French and Russian have. So the way you say, if a wolf came in, it would eat me. The way you'd say that in such a language is a device that we have in English as well, which is a wolf could come in, period, it would eat you. So you use what's known as modal anaphora. So there's this kind of cross-sentential anaphora that goes far beyond just pronouns, but that in fact tons of languages, possibly even a majority of languages out there in the world use, and that we use as well in English, and they use these cross-sentential anaphoric elements. So it seems to me that the way forward that you're pointing at here seems to be one solution to a rather deep and important problem of extending machine translation to other languages, that don't basically have, this central kind of Indo-European structure. So it seems to me that the significance is far greater than you're allowing, and moreover, it makes me sort of wonder whether the successes of machine translation that I've benefited from them. I work in France. My French is pretty good, but it's not always amazing. I use Google Translate and DeepL and all manner of other things, all the time. Super useful. I wonder if this isn't actually kind of an accident and, a success that has something to do with the fact that English and French and Russian and German are basically the same language, modulo these small things like gender appears all of a sudden and, a few sort of grammatical features that are missing in one language or another. But when we really zoom out, we end up in a situation where we can't look at sentences. We have to look at much larger chunks of text. I wonder if you could comment on what you think about this. Thanks.
Okay. Yeah. Thanks for the comment. Yeah, that's a great observation. I don't have too much to say beyond that. I mean, I'm clearly focused on these phenomena that we have, lots in languages that we have lots of data for. I mean, even talking about the data harvesting piece, right? So this sort of sentence mining piece is sort of fundamental to that. So that's, I think, been an inhibition to building systems for languages probably that match these characteristics you're discussing. So if you don't have that as a first step, I mean, actually, if you read like the CC Matrix paper, they complain about Thai. I think there's even a footnote or something that says like if anybody has a sentence breaker for Thai, and that's a bit easier because the problem there is there's no punctuation. So the task is, a semantic one instead of, or I guess a more deeply semantic task, and pragmatic task than it is for other languages. That's already a problem that sort of, breaks an operational assumption for building MT systems. So yeah, I mean, if we can move to the paragraph level in general, I guess that's a good point. It could open up sort of like, I don't know, it's a blinder in some ways being removed from your eyes, right? So yeah, thanks. That's a good perspective.
So we have a question from Francois Yvan.
Yes, thanks. Hi, Matt. Thanks for the great talk. I have a question and a comment. I mean, I think that the distinction you're making between generative and constructive, I mean, you can do both at the same time, right? You could do both generative and contrastive, and by generating the contrast. So if you have the correct references, some noun on the correct pronoun, you can also generate an alternation with a change of noun and a change of pronoun and see if the system actually generates the contrast. So, I mean, this is another way to make the things a bit more complicated. And this is a comment. The question is, all of this, of course, is embarrassing because the evaluation is data and language dependent. In fact, language pair dependent. So any hint how we could move towards having evaluation metrics that are language independent?
Yeah, that's tricky. I mean, there was the, I wouldn't call it language independent, but there's complex tool chain metrics. I didn't talk about blonde at all, mostly because we're not doing English on the target side. I think there's probably things you could do with maybe this is a place for application of large language models, looking at their internal state, for example, potentially. But I don't have strong ideas of how to do this evaluation in a language agnostic way. It would be really nice if we could come up with some way to just do document level evaluation that worked at a coarse granularity for lots of different languages or language families. It's certainly on our agenda, but we I think for the most part are just focusing on these nice data sets that people have been put together so far.
All right, do we have any other questions? If not, I do have a question. And it's sort of going back more to the discussion that you had on lexical cohesion, which was actually my data set thing. So where some of the examples required you to repeat the translated word in the target. So there are a couple of those. I think it started out with lemonade and had another one. So there were a couple of examples where it did depend on the source, and those ones depended on both the repetition in the source and in the previous context. So in these examples, the idea was to find context where you would need to repeat it. So there were some other ones where saying, I think it said, can you do something mad? And then the person says, is this mad? You know, you sort of need that repetition for actually to communicate the right thing. So I agree with you that these are particularly difficult examples. So they were designed to really test the systems. And that it might also be difficult to find lots of data that contains them, because sometimes you have a repeated word just because it's repeated, and sometimes you have a repeated word because it's necessary. Given that it's so difficult, how do you think that we could build a model to handle these kind of cases? So it wasn't the individual case, it was the more like the lemonade one, but is there any way of us creating synthetic data to create these, given that they're actually quite subtle in which cases you want to repeat? I mean, you could have a more extreme case where someone says, she said blah, 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 and then someone else says, what? She said blah, 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 and you clearly then want to repeat exactly that.
Yeah, I was hoping you could tell me the answer to that question. Yeah, it's really hard. I mean, we have tried, right? So we've tried like the tool chains that I think you applied and Rico applied in the ContraPro data set, which are actually pretty intricate, right? You run the CoRef system, and you're just chaining together all of these. You do alignment, you're chaining together all these pieces to get a set of examples out. I really kind of wonder if we're getting to the end of the purely automatic evaluation era, right? We do have, you could say in some ways we've never had that, right? We always had to translate data sets to get a reference. So that was a big piece of human annotation effort. So I think maybe like an approach where you use automatic methods to identify good candidates, and then you prune them down with human annotation and insight. That would be probably good. Because what we see basically is you come up with some heuristic to identify some of these, and just the precision is so low. It's just so many that don't fit what you're looking. They match the pattern, but they aren't the phenomenon. So I think if you could come up with high recall metrics, or high recall tool chains, apply them, and then do human filtering and annotation. It's a lot of, I look at these data sets and I wonder how much work went into these annotations. It's really pretty incredible. And I think we're probably just gonna have to keep doing that, which is also a trend in the field, right? Like all of these big models are just getting, we don't even really know how many human hours are going into annotation and refinement and so on. And I don't see that, I don't see an end to that in the near future for MT as well.
Okay. Yeah, that was the sort of the reasoning behind my little data set. So that was manually constructed to make sure that the examples were completely sort of clean and also balanced, so that the idea was a sentence level system, you had to get 50%. So I was interested to see that you kind of use that. And is it kind of one of the more challenging sets, and do you test it and use that in Microsoft, even though it's quite small? I was quite interested to see that.
Oh yeah, yeah. We're using that to test the English-French system.
Okay.
I think that the disk-eval MT set has a bit more. We need to look more deeply into that because even some of them require target site context, some require source. Probably the analysis should be broken down by that. And there is this tendency, right? Your new system gets it wrong in this one, and so you criticize the data instead of the system. So certainly guilty of that in some settings. But yeah, it's useful. You kind of I don't know. I feel like researchers sort of chase the metrics, right? So that's a source of criticism sometimes. Like it's the the street light, you're looking under where the light is. So let's just put street lights in the right place, and then can make some progress.
Yeah. Okay, great. It'd be great to talk to you about the test set if you want any, if you have any questions about it later on.
Oh, okay, yeah.
So are there any other questions? If not, maybe I can just ask a very quick final one. It's kind of linked to what Francois said about evaluation metrics. So there are lots of different ways of evaluating now. Is it still worth trying to develop metrics that output a single score, or is that something that we should abandon?
In the end, you need a single score, right? The question is deploy the system or not, right? So that's a binary decision. It's like it comes down to one score. So, how you produce that, I think, is getting more complicated. We have some other work with a colleague at Microsoft on trying to do high precision identification of just like the long tail errors that MT systems make, hallucinations or mistranslations of numbers and units and so on. I think those matter too, right? Like you might get let's say you get a comet point gain, but you're hallucinating 1% more and so on. I think we do need to take a finer grained look at system performance across more and more categories. And we need to be able to do it in a way that we can actually trust those. Like those metrics have to be high precision. I think you'd much rather miss things than do the California Proposition 65. I don't know if you're familiar with this. California puts this Proposition 65 warning on everything. It says, this is known to the state of California to cause cancer. So, but they put it on everything. So you just don't trust it, right? You ignore it. And we don't want metrics to do that, right? You want to get a metric that says if this piece is wrong, maybe it missed the other 10 instances, but the one it got is good. But then, yeah, you have to, maybe you have like a 10-way metric. You have to weight those and, make a decision at some point. So I would say the answer is yes and no to the end of single score metrics.
Okay, great. Thank you. So we don't have any more questions. So thank you again. I'm sure everyone's clapping behind their computer screens.
Yep. Yeah, thank you for the invitation.
Thank you very much.
Nice to talk.
And yeah, have a good day, everybody. Thank you, everybody, for coming. Right, I'll stop recording.